Welcome again to another TED seminar. This semester, we are doing a seminar about climate change and transportation. And today, we have the pleasure to have Professor Hao Wang here with us. Dr. Hao Wang is a professor and graduate program director at the Department of Civil and Environmental Engineering of Rutgers University. His research areas focus on developing sustainable, resilient, and smart transportation infrastructures through material innovation, computational modeling, and life cycle analysis. He has been PI and co-PI of more than 50 research projects sponsored by federal and state agencies in the US. He is the recipient of the Walter F. Huber Award from ASE in 2022 and an elected fellow of Engineering Mechanics Institute of ASE. Dr. Wang received his PhD degree here at the University of Illinois Urbana-Champaign. So welcome, Professor.
Okay, fine. Okay, it's an honor to be here, to be back. 12 years ago, I moved from here, learning the skills, knowledge, and the spirit, and joined Rutgers. 12 years at Rutgers. There are 16 PhD students graduated from Rutgers in my past 12 years. I told them they're not only graduated from Rutgers, they also have the spirit from Illinois. And I hope some of them will be having a chance to visit Illinois in the future. First, quick introduction about Rutgers, and hopefully some of you will be with us, either postdoc, either colleague, or either visitors. We're in the East Coast, kind of center between New York and the DC, so we can just drive to the TRB. And also we have Scarlet, which is our football court. And what's interesting about the Rutgers is, you know, Professor Newmark, the Newmark building in Civil, Illinois. He was born in New Jersey. He got his undergraduate from Rutgers, 1930. That was when I was interviewed by Rutgers. They told me, they said they want to hire someone from Illinois because Newmark was graduating from here. Okay, so for the research side, we also have a center which is more like we call CATE, Center for Advanced Infrastructure and Transportation. It's kind of a combination of the UTC and also other research activities. From 1996, CATE has been leading consortium for UTC, regional, tier 1, national. We were the regional until this year, and next year we are part of the national center led by the Perryville A&M University in Texas. So we're not leading again, but we're still part of the national center. And then at CATE, we do all kinds of activities, and my research mainly focuses on the infrastructure side, mainly on highway, but sometimes also with bridge and rail and also pipeline. So today we will give you a basically overview about the projects or findings or experiences we have in the past, also 12 years, combining a few PhDs, 4 or 5 PhDs work. They kind of towards the same direction, sustainable and resilient roadways. Not only just pavements, we're also touching the base and also even touching the right-of-way assets for some solar energy harvesting, for example. And hopefully we can learn from each other and also we can find future collaboration with ICT further. Quick outline, overview about sustainability and resilience. Probably everyone knows about that, but just wanted to give you still fresh. Some projects or findings we are using, looking at sustainability for climate change mitigation and adaptation. And also some recent work we are starting looking at how to improve roadway resilience to flooding. And also some energy harvesting work we have been doing for the past 5 or 6 years from roadways and bridges, actually second generation on that, and also summary and implementation. And sustainability, we all know that, right? Because we're talking about 3 pillar stones. And here we want to focus a little bit more on the greenhouse gas emission because this has been increased rapidly with the human activities for economic development. And then we all know this is like a blanket impact with the greenhouse gas emission. You will have the positive reductive forcing. So basically you are emitting more heat from the ground to the atmosphere. So in that case, increasing the air temperature, causing a lot of adverse effect, energy consumption for the building and also extreme events, the melting of the glacier, many things. And then you may wonder, okay, where are these greenhouse gas emissions coming from? So here's the data from EPA for the greenhouse gas emission in US. We can see at different sectors, 29% coming from transportation, and especially from roadway transportation, because we're talking about the fossil fuel usage as compared to other sectors. And then among them, 80% are carbon dioxide. So basically, in order to mitigate climate change, in order to reduce greenhouse gas emission, there are many things transportation can do. And then we go to a very, I would say like, not a new, but for payment of roadways, relatively new approach called life cycle assessment. Probably you all know that. We're trying to find out, okay, what's the environmental impact for a project or product. So in this case, we're borrowing this concept for roadway. We're really looking at what will be the environmental burdens, especially greenhouse gas emission during this whole life cycle. So for infrastructure project, you have raw material, production, transportation, among them, construction, use phase, and then maintenance, end of life. So we all know about that. And then you may wonder, okay, why should we do that? Right? What's the purpose we are using LCA? How that can help to mitigate greenhouse gas emission? First, you want to quantify it. You know how much greenhouse gas emission coming from your project. And then you can find a way to reduce it. And using this approach, you find out not only the total emission, but also you find out what's the emission at each phase, material, construction, maintenance, operation. And then you can see, okay, can I change something? Can I either use concrete instead of asphalt? Or can I use recycled or not? Or can I just change the geometry alignment of the roadway? In US, it's impossible because we only have very few new roads. But in developing countries, we have the chance to selecting different geometry alignment to reduce the excavation. Then you're reducing the hauling of the material, reducing greenhouse gas emission. So that's a huge excavation amount. And then also looking at the structure design, also maintenance strategies. We'll show you the examples. We are using this approach to really try to improve the sustainability, reduce the emission. First, from material side, actually, I found this chart from one of the early papers by Bacedo. I think it's very interesting because it gives you a rough overview what are the embodied energy or carbon in megajoule per kilogram or kilogram carbon dioxide per kilogram of material. Basically, you can know roughly, okay, what kind of embodied carbon energy each material has. So here, actually, concrete block is more like concrete, so cement plus stone. Cement is on the top, and then this asphalt here is more like asphalt mixture, and then you have the bitumen on the top. These are the more materials we're familiar with. But also, you look at it, this other material, glass, plastic, or like even steel, they are very, I would say, like environmental burden intensive. So in that case, if we're talking about reinforced concrete, or we're talking about polymer modified binder, we should not neglect them because even small amount of them can bring a lot of greenhouse gas emission impact. So in order to really mitigate that, industry already has moved ahead. So you probably have heard about EPD. Actually, now Federal Highway has a climate changing program. They're trying to encouraging the DOTs to using the EPD in the procurement process. So basically, they hope the industry will be able to submit either industry average or product specific EPD. So the EPD basically is like output of the LCA, but the kind of EPD focuses more like a material stage, we call it A1 to A3. So in order to produce 1 ton of the concrete or cement or this fly ash, what are the embodied carbon or other environmental impact for that? In that case, you have this label, like a nutrition label for your food. So in that case, you'll be able to really make it transparent. So in the procurement process, you'll be able to set a bar, say, okay, we want the EPD lower than this amount. Or we give a little bit incentive to the EPD, which has lower value. So that's something actually Europe has been implementing and US is trying to catch it. So in this case, we try to control the material side. Another one is the type of the payment. I mean, we are more focused on asphalt pavement, but don't forget, we also have choice for concrete. This is the interesting project that we work with the Power Authority. They are looking at the rehabilitation of the runway. And then they are looking at, okay, what are the choices we have and what's the life cycle cost versus life cycle assessment results if I'm using asphalt overlay versus concrete overlay. So the bottom one is something like at that time they're making the decision. So they give us the PMS data, give us the previous rehabilitation strategy. So in that case, we come out with a similar rehabilitation procedure. So basically, milling 3-inch asphalt tracks, 9-inch asphalt overlay. If you do this way, every 8 years, you probably will do milling overlay again. If you do concrete, you do a little bit small milling, but putting 18-inch concrete, and then you have very light repair. So we did actually an LCA for these 2 overlay strategies. And then we look at initial construction plus maintenance. We found out in the total, the concrete overlay actually give you less emission. This is for the overlay case. And then we did a little bit more exercise that, okay, if it's a new airfield pavement, so with the field design, which is the FA design software, you'll be able to design 2 pavement structure for the same traffic. And then we have 9-inch HMA, 12-inch base HMA base, and also plus another correctional base versus 20-inch PCC. So for the new pavement one, that's the top results. And you can see this case, you do have the PCC give you more emission, of course, including upstream and combustion. And then the result opposite. So that tells us we have to do case-by-case analysis. So you cannot generally say which one is better, especially looking at the functional unit. If you learn from LCA class, right? The same design will be able to satisfy the same function. So it's not a 1-ton asphalt versus 1-ton cement. It's the structure satisfy the same traffic, the same period. We're comparing asphalt versus concrete. And then we're getting different conclusions. So that really means if we can bring this decision making, considering this greenhouse gas impact, we'll be able to have more transparent or more systemically informed decision making. But this is still the material stage. And then look at the use stage, which actually I know ICT has many people working on that. In this case, we're looking at what's the fuel consumption in the use stage, for example, truck. And then we have aerodynamic drag force, we have mechanical loss, and then we have load resistance. I have particular interest in this because my dissertation at that time, 12 years ago, was looking at the type interaction. Although at that time was more focused on pipeline cracking. But later on, we start looking at the friction, noise stuff, and also load resistance. So that means if you do have 3% load resistance reduced, 1% reduce. So in that case, we'll be able to have corresponding greenhouse gas emission reduction. So how can we really use this concept to help us to reduce from the pavement preservation or repetition side? So first we have to quantify. So first we want to quantify what's the emission coming from use stage. Actually, here we follow the approach by Professor Kali and Professor Hao Wang's paper. We kind of modify the moose using the HPM4 model, so be able to develop an emission factor depending on the II and also speed. So basically, we have a surface, and also we did this for different car, also light truck, heavy truck. So be able to really to adjust this based on the traffic composition. And after that, the first exercise we look at the preservation. The reason we do that is because we think preservation is good with very least amount of cost and also material input. And that is mainly for functional restoration, improve friction, reduce the roughness, or reduce aging. If you look at LDPP data, they will show you have II increasing after preservation, it drops, have a jump, and then you go back to increasing again. And then actually the data shows you, depending when you apply the preservation, you'll be able to have different jumps and also have the model after treatment. So we use the data from 3 different treatment procedures. And then we come up with a model, basically follow this trend. It's not a perfect model, but generally capture the trend. And then we put it this way, okay, if I have the opportunity to select the timing to preservation, what will be the best timing? So what we did here is for different treatments, it's at project level. If I have the opportunity to do preservation at different application timing or year, what will be the carbon dioxide reduction as compared to nothing? So you're expecting with crack seal reduction very small, although the field data does show a little bit improvement for roughness. But with chip seal and the thin overlay, you have more reduction. But basically, you can see by playing the amount at the timing doing the preservation, you'll be able to have different reduction. So in general, for like a light treatment, chip seal, crack seal, if the initial roughness is getting higher, you probably will do it early. If your initial roughness is getting lower, you can do it later. This is because, as I just mentioned, the previous jump, after doing the preservation, II jump, is always have, it's depending on the previous II before the treatment. So in that case, if it's too good, even you do the preservation, the jump of the II is not that big. If it's too bad, the jump also, although it's getting bigger, but it doesn't compensate the increase of the whole II. So you do have an optimization of timing. So people actually look at this from cost point of view before, but I think that people kind of didn't look at it from the CO2 point of view. So at that time, we were able trying to find out for a pressure level what's the optimum timing. And at that work level, actually got a follow-up paper on that, which you can check the details. So that's the preservation part. And then we talk about, okay, the climate change, this will deteriorate the pavement, accelerate the life. And then you may have different stressors, we call it, basically the potential threats caused by climate change. This could be like slowly happening, like warming temperature or sea level rise, or could be having some extreme events, like heavy rain or just have a flooding. So we try to find out, okay, can we incorporate this one into our analysis? So one exercise we did is we try to using ME because at the same time we are doing the local calibration for New Jersey DOT. New Jersey is like started using ME. They are still using both design software. In a few more years, they will decide using ME. So we developed the calibration coefficients for New Jersey, and then we try to find out, okay, if I'm using the temperature data which coming from the climate model as compared to the current approach which using historical ME temperature. If you look at ME, they will tell you depending regardless which year you design, they're always using the temperature database from 1985 to let's say 2000. So repeating using these 20 years climate data, but they are not using really the future one because at that time maybe future one is having uncertainty. So now we're trying to say, okay, if we do have the predicted temperature, which actually is from the collaborator from Columbia, they are doing a local climate model. So we're trying to compare what will be the difference, and then any way we can mitigate this impact. So in this case, you can see first you have the temperature data coming from the future prediction. So left one is giving you the lower temperature. So you are seeing, okay, with the climate change scenario, RCP 8.5, basically it's carbon dioxide concentration pass. So it's assuming this carbon dioxide concentration will be able to causing 8.5 watts per square meter radiative forcing from the ground. That's RCP 8.5 means. Typically, they are using RCP 4.5, 6.5, 8.5, indicating different climate change intensity. So RCP 8.5 is a little bit more aggressive prediction. So you can see we are seeing the lower temperature getting less, we are seeing the high temperature getting higher. And then we put it into the typical New Jersey structure we have. In New Jersey, we mainly have flexible payments, composite payments. Here we use the flexible one, and it's pretty thick payment. So in this case, we're seeing although the writing is getting increased because of this temperature increase, but still within the limit. I mean, if you consider 0.5 inch or 1 inch is a limit, so it really doesn't control the failure. It's a particular cracking getting more aggressive. So in that case, your failure time getting ahead of time because of the climate change. And then you have the II also increasing. And the interesting that you can see, maybe instead of the 2 maintenance, you probably need a 3 maintenance. So what we did here is also look at the emission. One way we use the different from other people is we look at the emission. If you really look at climate people, they will tell you this greenhouse gas emission is not steady. They will decay with times. That means this number will reducing with a function. So we adopted the burn carbon cycle model, which give you a decay function. In that case, you do know, okay, if I do release this amount of emission this year, what will be the residual emission over the years? So we did that over year prediction, not just 1 point summation. So with that, you'll be able to get in the emission from construction and material stage, the top figure plus the use stage. And the reason you are seeing that jump is because of the overlay. So in that case, the left case is using the historical mirror. The right case is using the RCP 8.5. So in this case, actually you can see this temperature, warming temperature causes more repetition. That's why you're seeing 3 jumps. But actually the total numbers is not a big difference because the user stage also has some difference. So in order to better show that, we did the difference. So this case, you have the difference between RCP 8.5 minus merit. So that can be considered as the emission increase or reduction because of climate change. So this gives you a scenario. Okay, so for this life cycle with this treatment, if I consider climate change, is this emission will be increasing or decreasing? And then because we do the yearly trend, you just look at the final number, that'll be the number at the end of the service period. And then you can see if we do changing different overlay thickness and also changing the threshold to apply the overlay, you will be able to see different patterns. So interestingly, you are seeing at the overlay 6-inch, and if you do this overlay at the 10% particle cracking, you will be able to have actually a final negative greenhouse gas emission. Basically means at RCP 8.5, we're even having less greenhouse gas emission. So this gives you a hint. If I do play my overlay strategy and threshold kind of in a nice way, I may have the way to reduce the impact of the emission from climate change factor. Because in this case, although I'm doing early overlay and also a little thick overlay, but I'm reducing the roughness in the user stage. So in that case, that's why I'm still getting the final emission reduction. But again, this result is case by case dependent because the structure may change in the trend, also your overlay strategy change the trend. But at least that means we have the ways to play with it. I mean, you can find more details from the paper if you are interested. And then after we look at that, we also realize, regardless we do how much to reduce the emission, it's still happening, right? We are seeing warming temperature, at least in a different way, although regionally it's different, but still we're seeing this trend. So we are seeing some extreme events happening, especially in New Jersey. We have a couple of flooding events. So we try to say, okay, how can we at the same time to build infrastructure more resilient? And then you look at the definition for federal highway architecture. I mean, they are similar. Basically, first you try to do more work before it, anticipate, prepare, adapt, doing something, try to enhance your structure, or doing something within or after the disaster, right? Try to have the infrastructure respond to it or quick recovery. And then you are expecting we have some hydraulic spurring to the asphalt. Actually, these first two pictures are taken from New Jersey. First one was taken actually from the road on the slope nearby my house because that hydraulic pressure was able to pull the asphalt pavement out. The second one was taken from one of the coastal city because they have the sea level rise with tide flooding. So every year they're getting flooded for like 1 month. And then the community was trying to increase the road elevation actually every year. And then they're looking for some suggestions to solve the problem in a more effective way. The third one was from Wisconsin, actually. Wisconsin recently have some issue for the concrete bucket because they didn't realize the joint weight they have was not enough for the concrete to expand. So they're experiencing some buckling now. So in that case, there's some guidance from federal highway basically tells you if you want to design the resilient roadway, first you try to understanding what's the hazards, what's the possible threats from, and what's the risk of having them. If the risk is too low, maybe you don't need to spend too much effort because the effort of preventing it maybe is too high. So really depending which hazards have higher risk or which hazards have high consequence, you are deciding which one I will go for adaptation. So that's a general procedure they have. And then if you're really looking at the assessment approach from resilience, basically the basic definition, we modify the figure a little bit. So you are talking about performance level of the infrastructure getting down. That's because of disaster, and then you're getting recovered. And then depending which hazards or which recovery method you're using, you may have better performance, or you may have a same performance, or you may not even getting recovery because, for example, like sea level rise or warming temperature, just getting constant temperature increase slowly, or the groundwater table increase slowly. In that case, you still have the threat, just happen slowly. So based on that, we recently developed approach trying to looking at for flooding case, how can we better to quantify the impact and also develop some adaptation strategies. It's still ongoing work for one PhD and it's still halfway on that. So first we try to identify the intensity and frequency of this event, and then we modify the model we have before. Before we are already using viscoelastic asphalt, nonlinear bounded material, moving node, but now we're adding the moisture variation. Actually, you know the unbounded material modules is a function of moisture. And then if you look at the moisture distribution in the unbounded material subgrid, it's much more complicated than you are thinking. We found some LDP data we'll show you later. Basically, it's really up and down or changing. But in this case, we would be able to consider with a combined model, the modules of nonlinear and also moisture dependent, also metrics suction pressure dependent together. In that case, if you do have moisture content changing, because of the groundwater depth increase or the flooding, you'll be able to capture that the moisture changing. And then you'll be able to see, okay, even post the flooding, but I still have some moisture contents residual or increasing after the flooding, you'll be able to have impact on that. So first thing we did is we tried to define a scenario. So in this case, it's a paper we submitted this year for TRP, for to be accepted. So you're looking at, okay, we have the groundwater rise. This is continuously happening. We also have extreme precipitation happening. That's every 2 months. You have one high precipitation. We also have the flooding happens. That's in year 5 and year 20. And then each event you may come with the intensity of the events and also the moisture content changing. So these data are coming from the selected field data from literature or from New Jersey side. So in that case, you know the moisture content of the unbound material, how changing with the time. So here we're assuming asphalt is being really protected or sealed with crack, so there's no water coming from the asphalt pavement. In this case, we focus on the unbound material impact. And then we kind of extended the model we had before, adding a hydraulic part. So we'll be able to simulate if I do have a water head coming from the flooding or coming from the precipitation. And then depending the geometry of the road, how wide is the shoulder, and also if you do have vegetable or not, you can decide different infiltration coefficient, and then the water will be able to diffuse in the soil with the layer. Again, this is happening from the shoulder unprotected, unpaved part. We are assuming water only can come from the shoulder. Or you have a crack in the pavement, this water can come through. But for the paved one, the water is not able to come through. So with that, we'll be able to predict the moisture distribution. Basically, water will coming from the edge to the center gradually. And then this will change the nonlinear modulus. And then we kind of looking at, okay, with this very moisture condition, how that will change in the pavement condition. This case, assuming, for example, after the flooding event, actually the data has showing after flooding, the moisture will stay there, storing recovery. Takes about years, not go back to the original value shortly. So in that case, we kind of have a few scenarios. So black one is the baseline. So in this case, it's everything not happening. And then the red one, green one, both have the flooding, as we just showed, basically year 5 and year 20. And also sea level rise happening every year, basically for New Jersey, because we do experience the sea level rise over years. And then the green and the red one is assuming we have a short recovery versus non-recovery. This is because from field data, we are seeing the moisture may take about 1 to 2 years to go back to normal. So we kind of assume the 2 boundary extreme case. So you can see how this damage would be changing if you do have these different events. The damage factor was calculated with the traditional damage function, so we didn't do too much work on that. But response has been updated based on the moisture changing. So a little bit further down work is we're working with also DOT looking at, okay, after we have the flooding, can we open the road right away? They are worried about something like the subway is still wet. So in this case, if you open the roadway, it allows the heavy traffic to come in and also heavy traffic volume, it will accelerate the deterioration. But it's very challenging to measure the moisture condition after flooding. You can do that very costly. So ideally, I mean, they want to do FWD and then they have the deflection. So you can see the deflection will be increasing during the flooding, right after flooding, and then start decreasing as the water kind of proceeds away. But this trend takes some time. So we want to know, okay, what will be the threshold of deflection we can use kind of this way. And then we propose a different approach is instead of looking at deflection, we're trying to see, okay, can we transfer this deflection to response? So if I can find the relationship between the deflection and response, and then I'll be able to predict response from deflection. And then with the response, because I already have the damage function available, I'll be able to predict with this response what will be the damage if I allow heavy traffic for this month, or if I have some traffic control for this month, for the damage reduction for that. So in order to that deflection to response, ideally is you do have real data before and after flooding, but that's very difficult to get. So indirectly what we did is we go ahead and collect the real data from LDBP and other states with low in moisture condition, but there's no FWD, there's no response data, but we know the moisture condition, moisture distribution. And then we build a database. For example, this shows you some real data. at different sections, spring, summer, fall. So basically, we have about 200 sections with moisture contents. And then we try to see, okay, if I can build a database for this, and then I do the FWD simulation, and also the moving node simulation, I'll be able to get the deflection versus response relationship. And then with the assumption, after flooding, this moisture variation is part of that. So in that case, instead of back calculating the moisture content or modulus with the post-flooding data, we're kind of building ahead of database, and then we're building this universal relationship. Again, I mean, you have to be getting more data to be more accurate. But the idea here is, so with these various sections, we're building a relationship between the deflection and response. And after that, if I do have this deflection data available from the testing side, I'll be able to see, okay, what's the response if you're allowing this kind of truck in. And then if you do have the traffic warning, you'll be able to getting what kind of damage over this months. And then you will see, okay, if the moisture content, or depending on deflection, right? If the moisture content is getting higher, your deflection will be higher, and then it's not to be higher. So be able to quantify the damage. So we develop a model, basically have two post models. Actually, this model has been working since my PhD, so we just borrow it by adding this moisture variation. So you can see some correlation, pretty good correlation for deflection, tensile strain, but compressive strain is tricky because in this case, the unbound material is getting more complicated because moisture content variation. So the correlation is not that good. But for asphalt side and deflection side, surface deflection on the travel node, you'll be able to get good correlation. So with this relationship, if I do have deflection tested after flooding, I'll be able to transfer this to basically the critical strain. So in this case, you can see sample data before flooding, you have lower deflection, after flooding getting higher, and then 1 month, 2 months, 3 months, you are actually getting reduced deflection, but still not to go back to the previous level. So we can convert this to tensile strain, and then we look at it, okay, if I do allow the same traffic as before flooding, what's the damage factor will be? Actually, in this case, if we have about 30,000 easels per month, the damage caused by the pre-flooding case will be 0.001. But if you look at the damage here, because of the moisture event, this damage factor becomes 0.02 or 0.04. So in order to control, let's see, if you want to control, okay, I don't want this damage accumulated during the first month after flooding exceeding the months before flooding. So something you can do is either reduce the traffic volume or control the heavy weight. So you will be able to know, okay, what's the minimum allowable easel for this month. Again, that's the choice of the DOT side. But the idea here is you can do something to reducing the easel or improving the traffic level on the road right after flooding, depending your moisture content recovery or coming from your FW results. So that's something actually we thought is maybe a good approach, try to really preventing accelerated damage because the flooding issue caused the moisture variation. Okay, then go to the last topic. Is also recently completed the project in phase 1, and phase 2 is ongoing. Is trying to looking at getting energy from roadway. I mean, the idea is not new because many people work on that, but we try to see how to find a way to getting energy by making it useful and also have less disturbance with the traffic or existing infrastructure. Of course, you have the solar energy in the roadway, you have the kinetic energy, you also have a lot of assets around the roadway. So through the project, we kind of focus on 2 ways. One is looking at large scale. Actually, in this case, we're looking at solar energy, which is also not new at all. But we're trying to see, okay, how can we use the roadway assets, especially in New Jersey, actually, we're using noise wall because in an urban environment, we have a lot of noise wall, which actually we thought it's a good opportunity to get into solar energy. In this case, the energy can be fed back to the grid, even to create a lot of net metering saving in revenue for the states. And the micro scale is we are looking at the small scale. So in this case, milliwatt energy. So in this case, probably only can power sensors or one state transfer. So in that case, you'll not be able to really generate huge amount. Even you're putting a lot, still it's limited. So in this case, we're really feeding this energy for the sensor, providing the small amount of external battery. But at the same time, if you're using some piezo material, you can also use that sensor too. So that's actually the two focus area we have done in the complete project. So for the solar side, it's not a new idea, but depending which way you want to put it on the rest area, canopy in the rest area, or even with pavement, which has been tested in China. Maybe sidewalk is okay, but the travel lanes are challenging. And also people even proposing to build a solar tunnel. In that case, you even don't have the rain and snow. But the issue is the price, right? You have to build that to cover. So as we said, in this project, we focus on noise wall because New Jersey has quite a long mileage of noise walls, and also these noise walls actually are going to be retrofitted. So we're looking at what are the best way to combining the solar panel with the noise for the retrofitting design. So the goal was trying to find out what's the best design because you can see different panels can be put in. So we try to find out not only just looking at energy output, but also coming from life cycle point of view, because you also need to spend energy, spend money to produce the solar panel. So in that case, what's the return period for the produced energy to be equal or even higher than the energy spent to produce the panel? So in this case, we're talking about the payback time. So in this case, we want the benefits really produced to be equally and even greater than the expense you spend in the beginning. So we look at a few criteria. The cost side, what's the cost reduction? So in that case, what's the reduction from the solar energy generated, which will be the cheaper price solar to DOT, but also you are paying front of price to make the panel to install it on the noise. We're also looking at the green cost reduction for this process, and also the payback time to make this break even. So although the project was focused on New Jersey, but we did a little bit wider study for the US. We chose 4 different states and cities. They have different, they call it global horizon radius, basically indication of the solar intensity. And then you will be able to come up with a design. So that's a 4 design we do analysis, can put on the top, which is easy, but the area is limited, but you can do the tilting. And for the vertical one, you also can do the bifacial solar panel. In that case, both surfaces can carry or absorb solar energy. And then you can do the shingle one, which is the solar one. If you do the good spacing, you will be avoiding the shading and have large area. The fourth one we call a vertical build out. So basically just putting the panel directly on the noise wall, which is easy for installation and large area, but you cannot adjust the direction. So with this 4 design, there are software you can use, which you can just input the design, and then they have the embedded solar model from National Renewable Energy Lab, which basically give you the solar radiation data, and then depending on the design you have, you'll be able to get energy output. So that's the first step. We're looking at different design, at different location, what's the energy output? Here is the comparison between facing south and the east. It's 2 extreme sides. One is like an ideal case facing south, another one is this ideal case facing east. We don't have any face of the noise panel facing the kind of sun direction. And then after that, as I said, we look at the multi-criteria. So we look at it, with the most energy output, what will be the total energy benefits? So basically that's the difference between the saving from the energy from the solar panel minus the price of the panel and also installation. So that's basically after a few years, you're starting seeing the saving. But at the beginning, you're putting the money in. So in order to reach this break-even point, that's the payback time. That's why you're seeing the energy benefits. Also, you have an energy payback time. Similarly, for economic payback time and community NPV, and also for greenhouse gas saving and greenhouse gas payback time. So we did a little normalization. So in that case, some of them highest is better, some of them lowest is better. So this has been normalized. So in general, if you put this spider chart, you will see, highest area gives you the highest benefit for this design. And this is the case for facing south. So basically you can see, if you do have the, we call it the top mounted design, they may give you kind of shortest the payback time, but the total energy saving or greenhouse gas emission saving may not be as good as a shingle design. So depending in this case, which criteria you're looking at. If you are talking about long-term return, probably you go for shingle design. But if you're looking at just the short-term, to get a break-even point, maybe the top mounted design is okay. And we can find more details in this paper we published this year. But in general, we use this approach developed, and then we implemented for New Jersey. We selected a few noise pool, which has the highest potential for solar energy harvesting. And then we are trying to start a phase 2 to really kind of build a few pilot projects for that. The second part of this project is looking at a micro scale. In this case, we're looking at a small scale, and we work with the piezo because we kind of more familiar with the material. It's material changing the electric property under stress strain field. So depending which way you are looking at, it can be sensing or energy harvesting. And then you are talking about the PZT more for energy harvesting, PVDF mainly for sensing. And then in this case, you can do conversion mode or vibration mode. So either way, you are changing the stress strain. So we're causing the voltage, which you can convert to the current when you have a circuit. So we first look at previous design, including our older work. So people have worked on these designs, trying to put on the pavement. The simple as the disk. You can also make a beam. We did some piezo symbols, which is converting the conversion into tension early time, and also some recent work from Korea. They are using the PVDF composite, which make the bending, generating energy. So different designs have pros and cons. Energy can be changing, but the thing is, they have to be embedded. So in the discussion with DOT, they don't want to be digging. To be honest, they just said, okay, I don't want to put in something in, and especially for testing, they don't want to do that. And it happened also, we have another project working on the bridge side, which is the bridge accelerated testing project. So that's why it gave us a little bit of motivation. Actually, this recent project we just completed, instead of looking at the embedded one, we kind of looking at the vibration one. I mean, the idea is not new because people use the cantilever to generating piezo energy. But here we want to emphasize is if you're really looking at the lateral frequency of the bridge, it's not just one frequency. They're really multiple. So the major frequency may be 4 Hertz one, 10 Hertz another one, 20 Hertz another one, and then a few high frequency case. So it's really multiple frequency. And then for piezo energy harvesting for vibration, you have to match this hosting structure frequency with your resonant frequency or with your cantilever's own frequency. After you have this matching, you'll be able to get resonance, the highest vibration. So previously, people were looking at, okay, I'm matching one, but here we're trying to matching couple. I mean, we're not matching all of them, but we're trying to match more than one. So in this case, we come up with a design we call the multi-degree of freedom. So in that case, we are putting multiple mass of the beam. So kind of we make one beam to 2 or 3 beams. Each beam can be served as a separate cantilever. In that case, you have several resonant frequencies. And then we will be able to collect the acceleration data from the field, and then use the data to optimize this resonant frequency, and then come up with optimized design. So basically, that's the lab testing we first did. So you can see the cantilever here. The left one is 1 degree of freedom. The middle one we call 2 degree of freedom. So we're cutting a little bit in the middle to create the internal beam. And third one is we call it 3 degree of freedom. So we are adding more cutting. Of course, you can do more, but in this case, you have to consider the structural stability. So depending the piezo cantilever you have, you may not do those many. But the idea here is with 1 degree, you only have 1 resonant frequency. With 2 degree, you have 2. With 3, you have 3. So if I can match these 3 separate resonant frequencies into the bridge's host structural natural frequency, you have a highest energy output that's compared to 1. So we first did the lab testing, which basically verify or measure the resonant frequency. And then we conduct we call a multi-phase model. In this case, really it's not just the mechanics. It's also have the electrostatic and also magnetic field. So we'll be able to predict if I do have different mass, different cantilever beams, what's the resonant frequency. The reason we're doing that is we want to create a database. I'll be able to easily find what kind of mass combination I'm using. The mass basically it's the as shown here. Here is the mass we're talking about. So basically, you're putting the mass here, which is the mass called the vibration. So that's the mass you're putting. So this mass, the amount of this mass is very important to changing your frequency. Of course, I mean this size too, but we are fixing this cantilever size. So we create a model trying to see, okay, if I do have different masses, what will be the lateral frequency will be? So I can create as many cases to develop this relation. Because later on, we will have the frequency measured from the real bridge. So I can see, okay, then what kind of mass combination I'll be able to match this random frequency. Then in that case, this will be my preferred design. So that's the purpose of the model. Otherwise, you have to test all of the mass combination, and every time you have to build a new sensor. So with that, we also put on the bridge. I mean, it's not a real bridge; it's a full-scale bridge on a separate project, mainly looking at bridge stack iteration and also NDE. It's a separate funded federal high project for another party. But we are able to test this cantilever on the bridge. So we're putting the middle of the girder. And then in this case, we're putting the 2 degree and 3 degree. So first we are getting the accelerated signal as a bridge vibration under the moving node. It's a real tandem axle load. And then this is the acceleration. So this is the peak we're talking about in the frequency domain. And then we're trying to adjust the mass on the sensor to match this peak. So you can see the data here. The blue one is purely just using a random mass. And the yellow one is something after the matching of the mass. Why you have this variation? Because sometimes it's tricky because you may need 35.5 gram mass, but in the real case, you will not be able to get exact amount. So that's why you have a variation. But basically, you can see the high end towards the preferred design. So we'll be able to increase the energy output really significantly. I mean, of course, after changing the location of the girder, sensor putting at the location, and also the design, the size of the cantilever also will change. But the idea here is we'll be able to adjusting the mass, which is the easiest way to adjust for the cantilever, be able to match the host structure. And the kind of work is on phase 2 is really trying to link this one to a bridge sensor, which see this one can really provide the power to that sensor for this case. So in summary, we really used the lifecycle assessment approach. We try to integrate into decision making for design, for preservation, for replication strategy. And in this case, you'll be able to see is that possible to improve your application timing or your strategy threshold in order to reduce the greenhouse gas emission over the whole life cycle. We also try to start looking at how to really considering these hazards or the impact of hazards on the performance of the payment in order to develop some adaptive strategies. Currently, we focus on the post-flooding road operation strategies for now. And from the energy harvesting point of view, we believe that's an option, but doesn't mean you should do it for every road, every segment, because we want to make sure this doesn't affect the current traffic condition. This is to be an additional function. It's not a really, I would say, the essential function for the road. This may be some benefits causing some small actual effort, or not the, I would say, no negative effort, but bring some positive benefits. And finally, I think we don't have the one size fits all issue or solution for this sustainable and resilient roadway system. We really want to use our knowledge and try to solve the problem one by one and try to reach them. Thank you for the attention.
Okay, guys, do we have questions for Professor Wang?
Great to see you. I was curious on your hydromechanical analysis, you had the 2 plots and the damage. So I understand on the subgrade, there was a difference in damage on the short and long term, but I wasn't understanding why the asphalt, I think the left-hand side was asphalt, if I remember correct, why it remained, the damage is over. So if your structure is deteriorating, why wouldn't your surface?
I think that structure, we kind of mimic the one for New Jersey case. So that's for the pretty thick. So even the moisture content changing doesn't affect the tensile strength too much. Okay. Maybe you're feeling that when this case, short recovery, long recovery doesn't have a big difference. Even with the baseline, it's showing the difference, but not as obvious as the subgrade.
I see. And what is the unit of that damage and how is that?
Oh, that one I believe it's a damage factor. So basically, it's the we are using the common damage function. So that I believe that one is we use the common damage function. We look at the total allowable ESO, and then what's the impact changing for that. So that's why not as big. Again, that also indicates it's not as expected. I mean, because we're not talking about something really destroy the structure. We're talking about something really happened slowly, so it accelerates the damage but it's not really visible or makes the structure kind of feel right away. Yeah.
Thank you, Professor. At the beginning of the presentation, you talked about the decay of CO2 emission. So I was wondering, is this like for the life cycle, like at the end of the life cycle, we should remove some of the emissions from the beginning of the life cycle?
Yeah, that one, we didn't do deep research, but we did look at the literature from the atmosphere group. Basically, they are showing if you have CO2 generated this year, this CO2 will decay over years. So in that case, instead of summation, sum of them, regardless of the timing they are producing, we kind of did a time series. So we are marking, okay, at which year you are generating how many CO2, and this CO2 will be decayed. And then it's residual when we stay there and then adding another one. So in that case, the final one, if you look at it every year, you'll be able to have the CO2 produced every year. And then if you look at it over the lifetime, you have it over lifetime. I think previously people did is they just adding them together, regardless of the year they're producing, which will get the same trend. We compare the trend will be the same. The scenario A to B will be the same trend. A is greater than B in this case, but the amount changes. Yeah. So I will now say this is really changing the decision we had before, but just more accurately quantify the amount. Okay.
Thank you.
Okay, do you have any quick question?
Yes, I do, but it's small, sorry.
Okay.
Or was there a question? When you were doing the flooding analysis, you had 1 month, 2 months, and 3 months? Was it 1 month after flooding?
Yes, I think the other one talking about post flooding.
Yeah,
Yeah, that one was we're talking about 1 month after flooding, 2 months, 3 months. So basically, the moisture content will recover slowly after flooding. So we try to quantify. Let's see, in the 3 months is after flooding, if the moisture content is still not recovered to the original one, how this will affect the damage.
yeah. So I guess my question would be, why did you determine what month was the optimal versus closer to the days of flooding where saturation will be?
Oh yeah, you can do week, 1 week,
Right,
2 weeks. Yeah, yeah. That's just an example. So that's really depending on the decision making, right? If you want to do the traffic control or put the weight limit for only week or a month. So ideally, you can do more precise, but we just use a month to illustrate the concept. Yeah.
So that ends our session for today. Thank you.